Hey guys, Mr. McKinney here, just finishing up part 2 of the Unit 5 AP review. So we left off on this slide. Again, super important. Make sure you understand all this information. So we're going to talk about a few theorems or tests really, and then we'll look at the graphs and the relationship between f prime, and f double prime, and then we'll do some word problems at the end. So the first derivative test, I never call it the first derivative test in class, but this is the one you guys are used to. So if you're trying to find a local max or a local min, look for where f prime changes sign. So if f prime changes from positive to negative, you have a local maximum. If f prime changes from negative to positive, you have a local minimum. If f prime doesn't change sign, then it's not a local max or a min. It's still a critical point, but not a max or a min. So this isn't new, it's just a new name for what you've already been doing in class. Another way to find the local max or local min would be the second derivative test. So if the first derivative is equal to 0, then you look at the second derivative. So if the second derivative is negative, that means it's concave down, and that would mean that you're at a local maximum. If the first derivative is 0, but the second derivative is positive, second derivative positive means you would be concave up, and that point would be a local minimum. So I never talked about this in class. I think Mr. Jansen's did a little bit, but we never talked about the second derivative test in class. So if you want to find a local max or a local min, one way to do it is the first derivative test. Look to make sure that f prime changes from positive to negative or negative to positive. But another way to do it is the second derivative test. So if the first derivative is 0, then instead of checking to see if the first derivative changes signs, just look at the second derivative. If the second derivative is negative, that means your function is concave down, which would mean you're at a maximum. And then if your second derivative is positive, then you're at a minimum. The candidates test is what you would use to find the absolute extrema. So first derivative and second derivative tests will help you find local maxes or mins. The absolute max or min might be at a local max or a min, but it also might be at the endpoints. So when you're looking for the absolute max or min, don't forget to check the endpoints. Find your local maxes and mins like we've been doing, but then check the endpoints. So you just look at all the critical points and you look at the endpoints. Whatever the largest y value is, that's your absolute maximum. Whatever the smallest y value is, that's your absolute minimum. So that's what the candidates test is referring to. Basically just making sure you remember to check the endpoints in addition to local maxes or mins. I don't know what the name of this theorem is, but as I was working through all the problems you guys are going to be doing this week and then looking at the keys, one of the things they talk about is if a closed interval only has one critical point and that critical point is a local max or min, then it is also the absolute max or min. So consider this piece of a parabola here. There's only one point on this parabola where the derivative is equal to 0. So we've got a horizontal tangent line here. There's only one critical point, and since we go from decreasing to increasing, this is a local min. So if you only have one critical point, and that one critical point is a local max or a min, it's also going to be the absolute max or a min. In this picture, we're talking about a minimum. In this picture, we're talking about a maximum. Because the only way that there could be a point lower than this would be if this graph turned back down and went down here. But if it turned back down, then we would have had a second critical point. So this theorem, and I don't know the name of it, and you don't have to say the name of it, you just have to say this. If a closed interval only has one critical point, and that critical point is a local max or min, then it's also the absolute max or min. If you don't want to memorize this theorem or understand it, then just check the critical point against the endpoints, and that's another way to prove that this is the absolute max. Or you can just write this sentence out. All right. The next bunch of slides look at the relationship between f prime, and f double prime when we're looking at a graph. Keep in mind that f prime, the first derivative, will tell you the slope of the tangent line. So slope will tell you if it's increasing or decreasing. The second derivative talks about concavity. Concave up looks like a cup. concave down looks like a frown. All right, so this first problem, you've got f shown on the graph, and you want to sketch f prime. So go ahead and hit pause and try to do that. All right, let's see how you did. So if this is f, wherever f has a horizontal tangent line, and there's 3 of them, f prime, the derivative, should be 0. So these 3 maxes and mins match up with zeros on f prime. When the original function is increasing, the derivative should be positive. When the original function is decreasing, the derivative should be negative. So here's the 2 graphs separate, and here they are on top of each other. Again, horizontal matches with a 0 on the derivative. All right, next problem. Same original graph, but now this is f prime. Sketch the graph of f double prime. All right, hit pause and give it a shot. Hopefully it didn't take very long, because all I did was copied and pasted these slides and changed f to f prime and changed f prime to f double prime. The relationship between f prime and f double prime is exactly the same as the relationship between f and f prime. So if I look at the points that have horizontal tangents here on f prime, those are going to be zeros on f double prime. All right, now if you skip f prime is where it gets a little bit harder. So we're going from f to f double prime. So go ahead and hit pause. All right, so when you're thinking about f double prime, you're thinking about the concavity. So think about where it's concave down. So I'm concave down here, and I'm concave down here. That's going to mean that f double prime is negative on those parts. And then here, I'm concave up, so f double prime is going to be positive. And these points of inflection are going to be where the second derivative was equal to 0. So those are going to be zeros on the graph of the second derivative. So original function, second derivative. So again, we have 2 zeros where the POIs were, not where the maxes and mins are. And then f double prime is negative to start because we're concave down. And then f double prime is positive because we're concave up. And then f double prime is negative because we're concave down again. Now we're going to work backwards. So start with f prime, sketch a possible graph of f. It's a possible graph because when we're going backwards or when we're going up a level, you can shift it up or down, because if we had taken the integral, you'd have a plus c, and we don't know what that constant is. All right, let's see how you guys are doing. So when I want to go from f prime to f, this is telling me the slope. So let's look at it. Right here, I start out with negative f prime. So a negative slope means my original function is decreasing. The rest of the time, the slope or the derivative is positive until we get to the end. So if the slope is positive, because this was going down all the way to here, and then the slope became positive and goes up from here all the way to here. So this big box corresponds to this part where I am increasing the whole time. And then I start decreasing again when the derivative became negative, and this shows them at the same time. I'm not going to walk all the way through going from f double prime to f. Just think about concavity. So f double prime is negative. That means the original graph is concave down. It's negative here, so it's going to be concave down. Here, f double prime is positive, so the original function is going to be concave up. So I'm going to be concave down, then I'm going to be concave up, and then I'm going to be concave down. So it looks something like this. Concave down, concave up, concave down. Usually this would be a multiple choice type question, and there's no multiple choice this year, so don't worry about it too much, but take a look. The last thing we're going to talk about is optimization. These are very similar to the related rates problems where you're going to set up equations and take the derivative, but you're going to want to end up figuring out what either a maximum or minimum is. So you're looking for basically the absolute max or min. So we've seen this problem many times. We're making an open-topped box. It's saying that this is 8 and this is 8. So then if we cut out x from the corner, x would become the height, and then we've got 8 minus 2x and 8 minus 2x. So we want max volume, so we need an equation for volume, length times width times height. Height is just x. Length and width are both 8 minus 2x. I'm not going to show every single step, but you would multiply this out, and then when you find the derivative, set that equal to 0, and that's where a max or a min could happen. All right, so let's take a look. So volume, length times width times height. Again, worked it all the way out. V can simplify to this. Don't try to use the product rule 3 times. That's crazy. So you take the derivative, set the derivative equal to 0. The possibilities for where V or volume is at a max is where V prime is 0. So it could have happened at 4/3, it could have happened at 4, or it could have happened at the endpoints. In this case, the endpoints are 0 or 4, because if you cut out more than 4 from each corner, you've cut out the whole sheet of metal. And if you cut out nothing, you don't have a box. So in between 0 and 4. So I also need to check 0 and 4. I can fill in that the slope was 0 at these two x values. Since I go from a positive derivative to a negative derivative, I know that I'm at a local max, and then I need to check my local max with the endpoints. Since this is higher than both the endpoints, then I know that it is the absolute max. As long as you check the endpoints, you technically don't need to show this part, but it makes it a lot easier to go through your reasoning. All right, let's look at one last problem. So I have 1,200 feet of fence to build a rectangular cat enclosure. One side of the property has a cliff, so I only need to enclose 3 sides. Go ahead and hit pause and try to figure out what the most area the cats would have to roam would be. So in this case, 1,200 feet of fence is talking about the perimeter. Normally, perimeter would be 2L plus 2W, but in this case, I'm going to just say that it's L plus 2W because we don't have to build the fence on this side. We know that the perimeter is going to be 1,200 feet, so I'd say 1,200 equals L plus 2W. So L would be 1,200 minus 2W. I also want to know the formula for area because I'm trying to find the most area. Area of a rectangle is length times width, and then I know the length in terms of the width, so the area would be 1,200 minus 2W times W. Multiply that W in, so 1,200W minus 2W squared. To find the max or the min, you're going to want to look at the derivative, because then you can find where local maxes and mins happen, and then check the endpoints. So I'd have 1,200 minus 4W. I want to know when that's equal to 0. That's going to happen at 300. So I need to check when the width is 300 and then the endpoints. So I've got that all worked out here. Width would be 300. So I'd need to check the endpoints. So the least the width could be would be 0. That wouldn't really be much of anything. The most it could be would be 600, because if you took 600 for both the widths, there would be nothing left for the length. So I need to check 0, 300, and 600. The area, if the width is 0 or if the width is 600, is 0. And I get that by just plugging in to this equation for area. The area at 300, either plug in 300 to this equation or plug in 300 for the length and get that the length is 600. 300 times 600 is 180,000 feet square. So when you're finding the max or the min, just find the derivative, set it equal to 0, and then find the absolute max or min by checking the endpoints. Hope this was helpful.